So this section, we are breaking it up. It's going to take us probably 3 days to get through this. So probably Friday we'll do a quiz over section 4.9, the antiderivatives and stuff. That way we'll do one before we get into the last little section that we're going through. First, we kind of have some motivation. What are we doing here? What kind of problem are we trying to solve? Okay, we have looked at lots of different curves, but sometimes we need to be able to find the area under the curve. Okay, and in order to actually calculate the area, we have to have some parameters. So in this case, I'd be finding the area from A to B between the curve and the x-axis. So if I wanted the area of that blue region, we need to figure out how could I calculate that area. Do you guys have any ideas? How do you find areas in general?
Length times width.
Okay, if it's a rectangle, we can do length times width. If it's like, what if I gave you a house-shaped figure? You break it up. So you break it into things that you can find the area of. So like we have formulas for every rectangle, triangle, circle, those kinds of things. And we could break it up and add those together. Okay, so we know with irregular shapes, this is just kind of a refresher. Rectangles, length times width, area of a triangle, 1/2 base times height. If you have a weird shape, we break them up and add the areas together. But this curve, can I really break it up and create any of those? No. Okay, we could do some weird things, but even so, this is curved, so it's not going to be a true triangle. So any of the ways that we could find this area, they're not going to be exact, are they? We could kind of approximate it, but it's not going to be perfect. So we could try to approximate the area by using rectangles. So here I wanted to know the area of y equals x squared from x equals 0 to x equals 1. Now if I just did a big rectangle, would that be a very good area?
No, you're going to be good.
It'd be way off, wouldn't it? What if I just broke it into 2 rectangles? Like if I did this rectangle and then this one. Is that better? Better. Is it close? No. So what would make it close? 3 rectangles. And then how could you get closer than 3 rectangles? 4. And if I want to be closer than 4, we could do 5, 6. The more rectangles you use, the better your approximation. So we can, to get a better idea, we can use more and more rectangles. So this is kind of like when the number of the rectangles goes to infinity, right? So this is kind of like a limit idea. But we're not going to get to that limit idea today. We're just starting with more of the basics. What are we doing here? So we are going to use some rectangles to approximate areas today. But we're going to look at a set number of rectangles. So we're not doing an infinite number. We're going to keep it fairly manageable. So if I wanted to estimate the area, I want an under and an over estimate. We'll talk about that in a second. Of the area of the region f of x equals x squared on the interval 0 to 3. First, using 5 rectangles, each of a width 3/5, and then we'll do it with 10 rectangles. All right. So f of x equals x squared. What's that look like? Parabola. Okay. So we know, actually I'm not going to even be real precise on this. We know that in general, we're going from 0 to 3, and this parabola is just going to be going up, right? So the first time, I'm going to use 5 rectangles. How far is it to get from 0 to 3? 3. The distance is 3, right? The length is 3. And dividing by 5 rectangles, that's where the 3/5 comes from. All right? So we know to get area of a rectangle, it's just length times width. And how many of these would I be adding up? 5. Length times width. Okay, can we agree all of these rectangles, if I'm dividing them evenly, have a width of 3/5? So can I make my life, let's pretend that's 3, a little bit easier and put the 3/5 out here rather than writing it 5 times? Okay. So now that's the width. We need to figure out what the height of these rectangles is, each of those points. And we can do it a couple different ways. When I'm looking at the rectangle, I can either use the left side or the right side to estimate the height. Okay, so if I used this one to estimate the height of the first rectangle, okay, then all my rectangles would look like this. Would this be an over or an underestimate? Over. How do you know that?
Because it's over the line.
Alright, so I'm going to call this over. I'm going to put a little subscript 5. This is my overestimate with 5 rectangles. So, the height of these rectangles is measured by the point on my parabola. So this is 0, and we're going up by 3/5. So this would be 3/5, 6/5, 9/5, 12/5, and then 3. Right, so the first one, my x is 3/5, so to get the y, you plug it in, so it would be 3/5 squared. Would you rather use fractions or decimals?
Fractions.
Alright, so this is
Numbers.
3/5 squared to get the y value. Okay, so the next one to measure my height, I would have to plug my 6/5 in. So that would be 6/5 squared. The next one, my height was measured from the 9/5. And the 12/5. And the last one we were plugging in. Alright, so you're going to need a calculator to do these. They're all not nice and pretty. Alright, let's see what we get. I want to compare when I do my underestimate with my 5 rectangles. What's going to change?
We need 10 of those, so we split them in half.
Well, I'm not even there yet. I asked for over and under
I would bid.
with 5. So my width is still 3/5, and I'm still adding 5 things together.
But they're gonna be, oh, actually, I don't know.
Well, I need to draw the rectangles below it, don't I?
Yeah,
So my rectangles would be these. So, in other words, instead of using the right-hand side, I'm using the left. So what's the first x value that we plug in? 0. And then the next one is,
3/5,
and the next one,
6/5,
the next one, and the last one. So notice the only difference between these is the first and last. One of them started at your first endpoint, which was 0, and it ended before the 3. The second one started after 0 and ended on the 3. So there's only 1 point difference. If you just hit second enter, all you really have to do is go back and change that 3 squared to a 0. I got 6.48. So, where's the true answer? Somewhere between these two. One we know is higher than the actual, one we know is lower than the actual. So what should happen when I do 10 rectangles? Is it going to be better or worse? Better. Okay. So let's talk about the overestimate with 10. What would my width be on this? Okay, and then we're going to be adding 10 things together. All right. So for my overestimate, we would start not at 0, but at our first point, right? If we're going up by 3/10, can we do decimals? That might be easier. 0.3. So the first one we plug in 0.3 squared. And then we're just adding 3/10 each time. So 0.6 squared, 0.9 squared, 1.2 squared, 1.5 squared, 1.8 squared, 2.1 squared, 2.4 squared, 2.7 squared, and my last one is 3 squared, which is where it should end because that's my end point. Why am I squaring these? The function was x squared, so that means we're squaring. Okay, so if I plug this in, we got 10.395. All right, so that's better. So the underestimate, all that changes is the first and last point. Where should I start with this one? Yeah, so it's basically just taking out this 3 squared and changing it to a 0 squared. If you have it all plugged in your calculator, all you have to do is second enter and bring it back up and change that very last point. Is it okay if I don't write all of these out? So this one is 7.695. Notice these are a little bit closer together than our original two estimates. The true answer is still somewhere in the middle. So your best guess right now would probably be to average the two of them and find the middle. It's not going to be perfect, but it's better. If we need a better estimate than this, what could we do? 15, 20, 50, 100. We could just keep adding rectangles and keep doing this. The more rectangles we have, the better off our answer will be. All right, I want to try a few more of these, making sure we know how to set those up and use these rectangles to estimate it. Is this example okay? So I want the over and under estimate for f of x equals 9 minus x squared on the interval 1 to 3 with n equals 8. Okay. So first I'm going to find my change in x, or my width. This one we're only going from 1 to 3. So that's only 2 units long, and I want to divide it into how many rectangles? 8. So we get 2 over 8, so 1/4 or 0.25. I'm just going to say 0.25. I think plugging these in definitely might be a little bit easier. So my rectangles will all have a width of 0.25. We're adding up 8 things. To get those things, we have to plug into our formula, which is 9 minus x squared. Now, the only difference between our over and under is one of them starts at the first endpoint and one doesn't. So let's just do it this way. Let's start at 1 for the first one, and we'll figure out in a second which is over and under, okay? So if I plug in 1 first, then I have 9 minus 1 squared. Everybody with me here? And then what would the next value I plug in be?
1.25.
Right. And the next value? 1.5. You're just adding 0.25. So if I add 0.25, we get 1.75. Minus 2 squared. And the last one we plug in will be 2.75. So let's put this in and see what we get. Everybody should be participating. I didn't draw a picture on this one intentionally. How do you think I'm going to know which is the over and under estimate without having a picture to look at?
The big number and the little number.
Yeah, the bigger one's the overestimate, the smaller one's the underestimate. You're welcome to draw a picture too, and you can see that for sure. So when we plug that in, we get 10.3125. Now for the second one, what is the only difference going to be? So basically what you're going to do is you're going to come back, you're going to take off this first point, and you're going to add another one at the end. So my first point would be the 1.25, and then the others are all the same. And then we add in a 9 minus 3 squared at the end. So if you have it on your calculator, you just have to go back and change that 9 minus 1 squared to a 9 minus 3 squared. So I can see the first one was my overestimate, and this one is my underestimate. So change in x is 0.5, we all agree with that? So then that will be the number you're multiplying by, that's the width of our rectangles. And then the first one you could start at 0 and then you just add that change in x. So 0.5, 1, 1.5, 2, and 2.5. And you're plugging those into the equation for the x's, right? So if you put it in those, what do you get?
I actually got the right numbers. This is the first time I actually got the right.
So what changes in the second one? What's the first x value you use? And then the others all stay the same. But you just have to add one more on the end. So So this one would go all the way to 3. And what did you get when you plugged that in?
3.25.
Is that what everybody got?
That's what I got.
3.25? Okay. So this one would be my overestimate, and this one is my underestimate. We're looking at a picture, it's just whether those rectangles fall above or below the curve, but we also know the higher numbers you're over and lower numbers you're under. So the true area between this graph and the x-axis is somewhere between those. All right, is this okay? So I think we can probably get a feeling right now that this is not that difficult, but could be super time consuming if I gave you a lot of rectangles. So the next thing that this section goes into is some things that would help us add that up faster. Today we're just going to work a little bit with summation notation, not actually applying it to this yet, just talking about the notation and what it means. So summation notation, it has a sigma, looks like a big E type thing, and it'll say from I equals 1 to n. This is your starting and your ending point, and then what you're adding up. So you're basically adding up all those different terms. So if I said the sum from I equals 1 to 10 of I squared, what do you think I'm adding up?
I squared.
So the first time I is 1, so 1 squared. And then I just increases by 1 each time. So the next one would be 2 squared, 3 squared, 4 squared. How far do we have to go?
10.
All right, add that up for me. You guys hit 385?
Because I didn't enter, I hit clear.
Oh, well, that's helpful.
Could have just pressed, calculator.
Okay, so what about this one? What am I going to be adding up? What would the first one be? 1 plus 1. Can I go ahead and just write that as 2? And then the next one would be?
3.
The next one.
4.
And where will I stop? Right, you'll plug in a 7 and you'll get 8. So this would add up to 35. B 2 to the n power. So this is 2 to the first, plus 2 to the second, plus 2 to the third, plus 2 to the fourth, plus 2 to the fifth, plus 2 to the sixth. And 126. The last one is a little uglier. Okay, how many things are we adding? 5. Okay. So if j equals 1, we have negative 1 to the j plus 1, so negative 1 squared over 1 squared is 1. If j is 2, we get negative 1 cubed over 2 squared, which is 4. If j equals 3, we get a negative 1 to the 4th over 9. J equals 4, we get a negative 1 to the 5th over 16. J equals 5, we get a negative 1 to the 6th over 25. All that the top is doing is basically switching if it's positive or negative. If you take a negative and square it, you get positive. But a negative cubed is negative. So it basically gives me a 1 minus 1/4 plus 1/9 minus 1/16 plus 1/25. And this one is not real pretty. 3019 over 3600. Gorgeous. Alright, we're going to do one more slide and then I'm stopping for today. So I just want to see if we can write a summation notation. So we have to sum from I equals 1. Where would I stop? Okay. So these look just like they're the number. Right? 1, 2, 3, 4, 5, 6. So that's just I. But what's happening? The signs are flipping. How did we just see that happens? Negative 1 to a power. So negative 1. Okay, if I just did negative 1 to the I, then if I put in a 1, this first term would be negative. Is that what I want? So let's see if we do I plus 1. So if I put in a 1, I get 1 times negative 1 squared, which is 1. 2 times negative 1 cubed is negative 2. So does this work? Yeah. What would you write for this one?
The top number is 5.
Sum from I equals 1 to 5 of the top is 1 divided by I squared is what Logan said. You guys agree with him? Last problem of the day. How many terms am I adding up here?
9.
So we have the sum from 1 to 9. Can you figure out a pattern here? 1 is the same as the square root of 1. 2 is the same as the square root of 4. 2 radical 2 is the same as the square root of 8. 3 is the square root of 9. So this is just the square root of 5.